In the last lecture, we have defined the three-phase system with the help of these north and south poles. We place a conductor in between these north and south poles, and this conductor cut the magnetic fields, and it will generate the fields across this. Okay, as you can see right now, here A1 and A2 is a conductor which generate one phase, and B1 and B2 is a conductor which generates second conductor which generate third. Okay. So this is the formation of three-phase system. So as you can see, A1 and A2, two conductors which generate a voltage EM sine of omega t, and B1 and B2 is a second conductor which generate a voltage EM sine of omega t minus 120 degree. Okay, so as you can see right now, this is the first conductor A1 and A2 in red color. Then second is a blue color which represent with the sinusoidal waveform of B1, B2, and third one is a yellow colors conductor representing the third phase with the C1, C2. So this is the representation for second phase, and this is the representation for third phase. Okay, so in first phase 120 degree phase difference is produced. In second, we have represented Em sine of omega t minus 120, and in third phase we have represented omega t minus 240. Okay, have you understood this, how we have generated these phases? Now in the last lecture we have discussed this star connections with the help of these three binding A1, A2, B1, B2 and C1, C2. Next in this we have generated first phase using A1, A2, and second phase by B1, B2, and third phase by C1, C2. And this is called a star connection where finished terminals are connected together. So we have generated the voltages across these winding are called a phase voltages, whereas the voltages across these line are called line voltages. Same in case of current. Okay, so we have derived the equations for phase voltages and current for currents. So we have derived the voltage that line voltage is equal to under root 3 of phase voltage, where line current is equal to the phase current in case of star connection. And in case of delta connection, we have connected these three wires from start terminal to finish terminal, and these are the phases which generated across the phase winding. So these phases are called phase voltages, and across the line we generated the line voltage. Okay, and we have calculated the relation between the phase voltage and the line voltage. So what is magnet? As I have told you, magnet consists of north and south pole. Okay, what is magnetic field? In a magnet, from north to south pole is called magnetic fields. What is magnetic flux? The amount of magnetic lines of force set up in a magnetic circuit is called a magnetic flux. Okay, what is the unit for this magnetic flux? The unit for magnetic flux is Webers. So magnetic flux density at a point is the flux per unit area at right angle to the flux at that point. And this is some material. So when you place this material inside the north and south pole, so magnetic lines cut this material from particular area. Okay, let's suppose that this material cut these magnetic lines from this area. Okay, so how to calculate this flux density? We consider this much area. Okay, so this is called a magnetic flux density for the circuit. How we can represent permeability? Permeability can be represented by mu. The ability of a material to conduct magnetic lines of forces through it is called permeability of that material. Okay, the ability of a material to conduct magnetic lines of forces through it. Okay, what is magnetic field intensity? Magnetic field intensity. A force acting on a unit north pole and placed at a point in a magnetic field. Okay, so how you can represent it? Magnetic field intensity can be represented by H. So H is mmf divided by length of magnetic path. Ampere turns. Okay, so the magnetic pressure which sets up or tends to set up on magnetic flux in a magnetic circuit. Okay, or we can represent it work done in moving a unit magnet pole. Okay, or it is in webers. Okay, so have you understood this? What is magnetomotive force? Now next is reluctance. How you can represent this reluctance? Reluctance can be represented by S. So what is the reluctance? The opposition offered to the magnetic flux by a magnetic circuit. Okay, so when you use resistance, so resistance offer opposition to the current. Okay, so reluctance offer opposition to magnetic flux. Okay, so how you can represent this reluctance? S is equal to L upon A into mu naught into mu R. Okay, so L is the length, A is the area, mu naught and mu R is permeability. Okay,